Alright, this is an introduction to chaos and why we need it. I won't be going over why we need it, but I will be going over an introduction to chaos theory. It's a book by James Gleick, and I've composed an overview of the book called Chaos with the subtitle Making a New Science, and I'll give key themes and concepts. There will be about 7 of those concepts, and then I'll talk briefly about 6 of the people who were pioneers in regards to chaos theory, and a discussion of why the book matters in a conclusion. So, Chaos, Making a New Science, published in 1987, chronicles the birth and development of chaos theory, a revolutionary branch of mathematics and physics that studies systems that appear disordered but are governed by underlying patterns and deterministic laws. Gleick weaves together history, biography, and science writing to introduce complex ideas in an accessible, narrative-driven way. Key themes and concepts: first would be the butterfly effect, or sensitive dependence on initial conditions. It was popularized by Edward Lorenz, a meteorologist. Small changes in the starting point of a dynamic system can result in vastly different outcomes. Lorenz discovered this while running weather simulations on early computers and realized rounding a decimal changed the entire forecast. This concept challenges the idea that if we know all initial conditions, we can predict the future precisely, which is a core belief in classical physics. Second would be fractals, introduced by Mandelbrot. Fractals are complex geometric shapes that are self-similar at different scales, found both in mathematical constructs and in nature. Coastlines, for example, mountains, clouds, ferns, or plants. Fractals provide a way to describe irregular, fragmented patterns that classical geometry cannot handle. Then there is nonlinear dynamics. Many natural systems are nonlinear, meaning their output is not directly proportional to their input. Chaos theory arose early, or partly from the realization that traditional linear models often fail to describe the true complexity of natural phenomena like population growth, weather, and turbulence. Fourth would be deterministic chaos. Chaos does not mean complete randomness. Chaotic systems are deterministic. They are governed by rules, but they are unpredictable due to their sensitivity to initial conditions. This idea revolutionized how scientists thought about predictability in the natural world. Then there is strange attractors. Discovered in the study of chaotic systems, these are patterns in the phase space, which is a graph of all possible states of a system. Unlike fixed points or periodic orbits, strange attractors are irregular, but they still follow a pattern. Lorenz's butterfly-shaped attractor is the most famous of this. Universality and scaling. Mitchell Feigenbaum discovered that systems undergoing a transition to chaos through a process called period doubling follow the same scaling laws, regardless of their physical makeup. His discovery of Feigenbaum constants showed that there is order within the onset of chaos. And then interdisciplinary impact. Chaos theory has applications in a wide array of scientific fields, such as meteorology, where it helps with weather prediction, biology with population dynamics, economics with market fluctuations, engineering with turbulence and oscillations, and medicine in heart rhythms and brain activities. Edward Lorenz, again, is the meteorologist who first identified the butterfly effect. Mandelbrot, a mathematician known for fractals. Feigenbaum, a physicist who quantified universality and chaos. Robert May was a biologist who explored chaotic behavior in population models. Stephen Small, a mathematician who developed abstract dynamical systems, and James York, first to use this term chaos in a scientific paper. The book matters because it brought a complex niche area of science into the public eye, helping scientists across disciplines recognize patterns in what had previously been dismissed as noise. It also challenged the dominant Newtonian worldview that assumed predictability and control. In conclusion, Chaos, Making a New Science is more than just a history of chaos theory. Its philosophical reflection on science itself is important as well. It questions the limits of predictability, the nature of patterns, and how we understand complexity. This storytelling helps non-experts appreciate how beauty and order can arise from apparent disorder, and how the smallest changes can reshape the entire world. And so that is the first part of Chaos, the introduction.